Hello, AP Chemers. Hope you're having a wonderful day. We just got done going over chapter 10, which talked about gases. So the next unit, chapters 11 and 12, talk about condensed states of matter, which are liquids and solids. So let's start with a brief comparison of solids, liquids, and gases. If we look at a particle diagram of each of the states of matter, you'll see that gases, the particles are really far apart. Remember, they're moving very fast, very randomly, and it's mostly empty space between the particles since they're so small compared to the spaces between them. Whereas liquids and solids, if you look at their particle diagrams, they're very condensed together. They're very close to each other, and so that's why we call it condensed states of matter. As you can see, the solids and the liquids are very similar in how far apart the particles are. The biggest difference is that solids are in this nice orderly crystal where the particles are in rows and columns. They make a very nice crystal, whereas liquids, they're kind of random. The movement of the particles in solids, they are stuck in their place in that nice crystal lattice, and so they vibrate in place, whereas liquids, the particles are free to slide around each other. That's why solids keep their shape, because the particles are stuck in their place. They can only vibrate, whereas liquids can slide around each other, so they can take the shape of the container. And of course, like we mentioned, gases are just moving around really crazy, going super fast and very randomly. So the density of solids and liquids are typically very close to each other. Maybe for most substances, solids are just a tiny bit more dense. For example, let's say you were melting wax to, pour it in to make a candle or something. If you have melted wax and you drop a piece of solid wax in it, the solid is just slightly more dense than the liquid, so it's going to sink to the bottom. That's what normal substances do. If you do the same thing with a piece of copper, solid, putting it into liquid copper, the solid will sink to the bottom because it's slightly more dense. Whereas with gases, they are way, way less dense than solids and liquids. Of course, the density, there's an exception to that between liquids and solids, which is water. Water, because of the hydrogen bonding, which we'll talk about a little bit more, the liquid is slightly more dense than the solid. But again, their densities are very, very similar to each other. So a couple of chapters ago, we talked about bonding. So we have intermolecular forces and intramolecular forces, and these are two words that people sometimes confuse on the AP exam. So remember, the word intra means within. So these are forces of attraction. Remember, in chemistry, forces mean attraction or repulsion. In this case, we're talking about attraction. So we're talking about attracting or attraction forces within a molecule. And so those are going to be your bonds, whether they're ionic or covalent bonds. So if you look at a molecule of water, for example, right here, the red is representing the intramolecular force. They are the forces of attraction within the molecule. And so those are the ones that hold the atoms together within a molecule. So those are the actual bonds. Whereas intermolecular forces, so inter means between. So like international means between nations. So intermolecular means between molecules. So those are forces of attraction between molecules. So if I have a water molecule right here and another water molecule right here, those are attracted to each other. When water, for example, it's raining and you're driving on your windshield, you see drops of water. It doesn't go completely flat. And so water has high intermolecular forces. That's why it forms drops. That's because the particles are so attracted to each other. So it has a pretty high surface tension, or, the molecules clump together or are attracted to each other. So there are different types of intermolecular forces, as well as different types of intramolecular forces. We already talked about the intramolecular forces, or the bonds. We said there's ionic, covalent, and metallic. And we said that that's determined by the electronegativity, or the difference in electronegativities between the two atoms that are bonding together. And so, remember we had like a continuum, and on one extreme we had nonpolar covalent, where the electrons are being shared 100% equally. On the other extreme we have ionic, where there's such a high electronegativity difference. So that's when you have complete giving and taking of the electrons. And then in between are your polar covalents. So these are the intramolecular forces, and we already, like we mentioned, talked about it in the previous chapters. Intramolecular forces are way, way stronger than intermolecular forces. If you think about it, if you have water at home, for example, it is very easy to break apart the attraction between the molecules, the intermolecular forces. All you got to do is heat it up a little bit. Put some water in your kettle or put it in a pot and heat it up on the stove, and your intermolecular forces are going to break apart. So your molecules are going to separate, and instead of a liquid, it's going to turn into a gas where the particles are really far apart. With intramolecular forces, these are really strong, though. That is very hard to break a bond compared to, the intermolecular forces. So if you take water at home, it's very hard to break the bonds and turn it into oxygen gas and hydrogen gas. You'd need like an electrolysis machine or something in order to do that. So intramolecular forces, way, way stronger than intermolecular forces. In gases, remember Chem Ch said that gases have no intermolecular forces. Well, that is not 100% true, but it's a good assumption because the particles are so far apart that attraction is not significant. However, with solids and liquids, the particles are close enough that the intermolecular forces will become significant. So we need to revisit or study the intermolecular forces and their types again. So there are 4 types of intermolecular forces within a substance. So within the molecules of the one pure substance, these are the 4 types of intermolecular forces. We have ionic forces or ionic interactions, dipole forces, hydrogen bonding, and London dispersion. So let's briefly talk about each of these. The next slide that I have here is not in your notes. So these are the types of intermolecular forces that are within the molecules of one substance. What if you have a mixture? So what if you take 2 substances and mix them together? Here are your options. So let's say you have, for example, NaCl, and you dissolve that in water. We'd say that these are called ion dipole forces. So ion because you have an ionic substance, and then dipole forces because you're dissolving it in a polar molecule. So these are interactions between 2 different types of substances when you mix them together. You could also have hydrogen bonding interactions. So that would be, for example, let's say you take some ammonia and you dissolve it in water. Both of these have hydrogen bonding interactions together. And a lot of times, actually, we'd call that hydrogen bond interactions to distinguish that those are 2 different substances. Next type is dipole-dipole interactions. So those are when you have two polar substances. So sometimes we can call this actually dipole-dipole interactions since they're both polar. Or let's say, you can say you got sugar and water. That would also be called dipole-dipole interactions because you got two polar molecules mixed together. Next type is called dipole-induced dipole. Induced dipole is another word for London dispersion, basically. And so this is if you have a nonpolar molecule and you're trying to put it with a polar molecule. We know that they don't mix very well, but there are very, very little interactions between them, very, very little attraction. For example, iodine in water. I don't know if you've ever used iodine. A lot of times we use iodine dissolved in water to like clean wounds. If you get cut or something like that. If you ever used iodine water, it's actually brownish in color. Iodine is purple, so if you take iodine and dissolve it in hexane, for example, since they're both nonpolar, they're going to mix very well, so you're going to get a purple solution. If you put iodine in water, very, very little of the iodine will dissolve. Last year we said that they would not dissolve at all, but in reality, very, very little of it dissolves. And so we call that interaction between the two dipole-induced dipole. Water is polar, so we call it dipole, and then iodine is nonpolar, so we'd say it's an induced dipole, which really means London dispersion. And then the last type is London dispersion forces, or you can call it induced dipole. Again, that means the same thing. So that's when you have two nonpolar molecules together. So that would be something like iodine in oil or in hexane, where they're both nonpolar. But this is on Google Classroom. So you'll find this PowerPoint on Google Classroom. So the first type of intermolecular forces, by the way, intermolecular forces are also known as van der Waals forces. Remember, like the real gas equation was called van der Waals equation. So intermolecular forces are also called van der Waals forces. So first type is ionic interactions. So that occurs obviously between ionic substances. So let's say you have some NaCl. So here's one formula unit. Remember, formula unit is the same thing as molecule. Of NaCl, it's made up of Na plus and a Cl minus. Here's another one, also made up of Na plus and Cl minus. So because this is made up of ions, some positive and some negative, the positive ion of one formula unit is attracted to the negative ion of the other formula unit and vice versa. So because you got positives and negatives, those are attracting each other. Out of the intermolecular forces, these are the strongest intermolecular forces. So that's for ionic substances. For covalent, you got three types. There's dipole, hydrogen bonds, and then London dispersion. So let's go with dipole. So dipole, if you remember the word di means two, pole means sides. So dipole means two sides. So these occur in polar molecules or molecules that have dipole, so sided molecules. And so if you remember, those are the ones where you have one atom more electronegative than the other, so it pulls the electrons towards it more. And so you have two different sides of the molecule because let's say you have, for example, HCl. Chlorine is more electronegative. It pulls the electrons towards it more. So the electrons are spending more time with the chlorine, and electrons are negative, so that gives chlorine a partial negative and hydrogen a partial positive. So if you look at this picture here, so in this case, the partial positives, let's say this is HCl, so that would be HCl right here. We'll just label a few of them. And so let's take a look, for example, at this hydrogen right here. And so this is partially positive. And so it's going to be attracted to the partial negative of all of these neighboring molecules. So it's attracted to the partial negative of this one, to the partial negative of this one, the partial negative of this one, and so on. And vice versa. So this chlorine, for example, right here is attracted to this hydrogen. It's also attracted to this hydrogen, and also attracted to this hydrogen, and so on and so forth. So it's the same idea as the ionic, except it's weaker because it's only a partial positive and a partial negative as opposed to a complete positive or a complete negative. All right, so that's dipole. Next type is called hydrogen bonding. And these are a special type of dipole. So these are special dipole. So they also occur in polar molecules, but they are special polar molecules. They are only the polar molecules that have an HF, HN, or HO in them. Because HF, HN, or HO are extremely polar bonds, and so their partial positive and partial negative are just a little bit stronger than a regular partial positive or partial negative in a normal dipole molecule. And so they're a special type of dipole. They're just slightly stronger than a regular dipole. And so if you look right here, for example, here's one water molecule, here's another, and here's another. And so oxygen is more electronegative than hydrogen, so it gets a partial negative. The hydrogens get a partial positive. And so the partial negative end of one, so this oxygen is attracted to the partial positive end of the other, and so on and so forth. So it's just like dipole, slightly stronger than dipole because it's a special type because, again, the partial positive and the partial negative are a little bit stronger. The name of hydrogen bondings is very misleading because you think it's a bond based on its name, but it's really not. It's not the actual bond that's within the molecule. It's not this right here. It's the attraction between two different molecules. All right, next type is London dispersion. London, that's a name, by the way, not the city, but the name of a person. Dispersion talks about the dispersion of electrons or the movement of electrons. So the idea is these occur in all of the molecules. Every single molecule has London dispersion forces. However, they are not significant unless it's a nonpolar molecule. Because if it's ionic or if it's polar, then you have either ionic interactions or dipole or hydrogen bonding, which are way, way stronger than London dispersion. So it's negligible in any of those. It's only significant in nonpolar molecules. These are very, very weak. And like I said, they occur in all molecules. The larger the molecule, the stronger the dispersion forces. And by larger, we actually mean the more electrons that it has, because the more electrons it has, the more the dispersion of those electrons or the movement of those electrons. The idea is, let's say these are two chlorines, for example. So there's a Cl2, there's another Cl2, and so you can see that their electron cloud is about evenly distributed since it's a nonpolar molecule. And so the electrons are moving randomly, very, very fast in these molecules. Just for an instant, sometimes those electrons are in one area of the molecule more than another. Just by coincidence and just momentarily, just for an instant. And so for that one instant, the molecule looks like this, where there are more electrons in this area than there is in this area. And so for that instant, you get a partial negative, a very small partial negative, and a very small partial positive. So what happens then is that the neighboring molecule does the exact same thing. The electrons are pushed this way so that they're here. And so now there is a slight force of attraction right there between the partial positive of one molecule and the partial negative of the other molecule. So again, it's all the same thing. It's the positive and negative attraction. It's just because this happens for an instant and then it goes away. That's why it's very, very, very weak. So to review, we have ionic interactions which happen with ionic molecules. Then for covalent, we could have dipole, hydrogen bonding, or London dispersion. So dipole is for polar molecules. Hydrogen bonding is for polar molecules that have an HF, HN, or HO. And then London dispersion is in all molecules, but it's only significant in nonpolar molecules. So if you're given a molecule or a compound and you want to know what type of intermolecular forces you have, the first thing you would ask yourself, is actually not in here, is if it's ionic or covalent. And so if it's ionic, then it has ionic interactions. If it's covalent, then you ask yourself, is the molecule polar or not? If it's not, then the only type of intermolecular forces it could have is London dispersion. If yes, if it is polar, then it has London dispersion and other things, but the London dispersion is negligible. The other things it could have is either hydrogen bond or dipole. So to know that, you ask yourself, do you have an HF, HN, or HO? If yes, then it's hydrogen bonding. If no, it is dipole. So that's a real quick review of intermolecular forces. Again, I know you don't have this page in your notes, but this PowerPoint is online on Google Classroom. So we're going to look in detail at these interactions or intermolecular forces that happen between two different substances when you mix two different substances together. So we're going to look at each of those that we talked about in detail. So the first one is ion dipole. So again, that would mean an ionic substance dissolved in a polar substance. So an example of that, like we mentioned, would be NaCl in water. And so when you take NaCl in water, so you start with NaCl, remember that an ionic substance dissociates in water, so the water physically gets in between your ions. And so what happens is you got this crystal made up of the Na pluses and the Cl minuses. And so what happens is the water comes in and surrounds the Na plus ion that's on the outside. And so water is polar. Oxygen has a partial negative, and so the oxygen portion of the water is attracted to that Na plus. And so since there's an attraction right here, if you get enough water molecules, enough oxygens with partial negative charge, they will be able to pull away that Na plus away from that crystal lattice. And so basically it's going to be pulled away and it's going to look like this. So there's your Na plus and it's surrounded by all these water molecules. And again, notice that the oxygen end is next to that sodium ion. So it took away that sodium ion. So I'm going to go ahead and Okay, then the same thing happens with the Cl minus. So here's your Cl minus right there. And so now the water will surround it from the other side with the hydrogens next to that chlorine, because the hydrogens are partially positive and the chlorine is negative, and so now there's an interaction between those negative chlorines and the positive hydrogens, and so those hydrogens, if there's enough of them, will be able to pull away that Cl minus from the crystal. And so here's your Cl minus. It's a little bit bigger than the Na plus in size. And then here are your water molecules surrounding it. And this time the hydrogen ends are the ones that are next to the ion. So now that you remove these two ions, you've cleared up the path for more water molecules to come in and grab the rest of the ions in the crystal until all of it dissolves. So when you stir, you're just speeding that up. You're speeding the process of getting those water molecules to surround those ions. And that's also why when you dissolve salt in water, you don't see the salt anymore. It's still there. It's just that each ion is surrounded by a whole bunch of water molecules, and these ions are super small, of course, but they're surrounded by a whole bunch of water molecules, so all you see is the water. So, based on what we just talked about, solvation, which means dissolving, involves two things. So, it involves dissociation and hydration. Dissociation means the actual breaking apart of the crystal. So the crystal taken apart. You know, so the Na pluses separated from the Cl minus and so on. So that should be endothermic because you have positives and negatives attracting to each other. So in order to separate those, you got to put in energy in order to take them apart. And remember, lattice energy, that would be like the opposite of lattice energy. So the ionic substances that have the really high lattice energy, so it's very exothermic in order to put these ions together. So then it's very endothermic to break it apart and take them apart. So you got the dissociation where the crystal is being taken apart, but also the other part is hydration. So hydration means that the water molecules surround the ions, just like we saw with the example above. And so that is exothermic. Because you got attraction, like we just saw between the water and the ions, whether it's the positive ion with the oxygen end or the negative ion with the hydrogen end, you got attraction. And so surrounding the water and the ions, that would be exothermic. The larger the ion, the less soluble it is, because then you have a harder time surrounding it. The smaller the ion, the easier it is to surround it, and the more exothermic. And so when you combine these two processes together, that's when you get solvation or dissolving. And so that's why the heat of dissolving or the heat of solvation can be either positive or negative depending on which of these processes is a larger number of joules. So that's why some substances are more soluble than others. So that's why it says here that this explains the solubility rules. All right, so let's write that down here, that the larger the ion, the less soluble, the smaller. Say smaller. I'm sorry, my stylus is lost, and I'm using a really small one, so it's very hard to write with it. The smaller the ion, the more soluble. So let's take a look at some substances, and we want to know which one is more likely to have a hydrated cation. So which of these would be most favorable to be hydrated? And so lithium sulfate or cesium sulfate. And so the one that you should pick would be lithium sulfate. That's because it has a smaller ion, so it's easier, more favorable for water to surround it. How about NiCl2 versus RbCl? So that one would be the nickel. All right, the next type of interactions between two substances is dipole-dipole forces. So based on the name, that tells you that you got two dipole molecules or two polar molecules mixed together. So an example of that would be, for example, sugar and water. So let's say that you have a, let's write down sugar, sugar in water. So let's say you got C12H22O11. That's sucrose or table sugar, and so that's a polar molecule. And so let's say this is slightly negative, this is slightly positive, and so same idea. The water is going to be attracted to it as well, and so on the negative end, the hydrogens will surround your sugar molecule like this. And then the positive end will do the opposite. The oxygen portion of the water will be attracted to it. And so each of these sugar molecules, for example, will be surrounded by a whole bunch of water molecules. So again, when you dissolve it, you don't really see the sugar molecules because each individual sugar molecule is surrounded by a whole bunch of water molecules, so all you see is the water. So this explains the solubility of polar covalent molecules and the insolubility of non-polar covalent molecules, and so that's what we used to call like dissolves like. So if you remember, polar substances dissolve polar substances, non-polar substances dissolve non-polar substances. So that's why we said like dissolves like. These two are alike, so they are soluble in each other. These two are alike, so they're soluble in each other. If you try to combine a polar and a non-polar, those would not dissolve together. The reason is, if you have a polar molecule, like for example, oil and water, water is polar, oil is non-polar. What happens is the water molecules all attract each other because you got these partial positive and partial negative ends attracting each other, and so all the water molecules are going to clump together because they have such high attraction to each other, and the non-polar molecules are just going to sit there. If you remember last year, I had the polar molecules represented by a bunch of magnets, and the non-polar molecules represented by marbles. And so if you take some magnets and some marbles, try to mix them together, they're never going to mix because all the magnets are going to stick together just like the water molecules will stick together. All the marbles will just sit there just like the oil particles because they're just not very attracted to each other. And so, you know, when you mix oil and water, it might seem to you like the oil is all clumping together but it's actually the opposite. It's the water that's clumping together and attracting each other, and the oil is just sitting there. All right, so let's look at this question here. It says, which would be soluble in water and why? We got CO2, NH3, CH3OH, and then this is called ether, diethyl ether. Let's start with CO2. For some of these, it's a little bit tricky because you actually have to look at whether they're polar or not, and to do that, you need to know their shape and be able to draw their Lewis-dot structure and so on. And so CO2 looks like this. If you remember, it's linear, it's nonpolar. And so since it's nonpolar, the answer would be no, it would not dissolve in water. NH3, we know that that one's polar. So the answer is yes. NH3 has 3 hydrogens attached to it, and then don't forget your lone pair there. And so that was meant to be 2 dots there. And so that's a trigonal pyramidal, remember? And so that is polar, so yes. CH3OH, if you draw that, I'll draw it on the side here. There's... and so that is definitely polar. So the answer is yes, those will mix. Dimethyl ether, this one right here, that one's tricky. I think if you put that on the AP exam, they'd accept actually either answer. I think the more correct one is that it would dissolve, because that is polar, although some organic chemists say that it's nonpolar. The reason why it's polar is, remember, you got 2 lone pairs there, so in reality it looks like a bend, just like water does. And so that is polar, so the answer would be yes, it would dissolve. Take a look at this statement right here. It says the greater the dipole moment, the higher the boiling point. That means the more polar the molecule is, the more or the higher the boiling point. So this is absolutely true, because the more the dipole moment, that means the more polar it is, the more the partial positive and the partial negative. So the more the attraction between the particles. And so if particles are really attracted to each other, it is harder to boil them or to get them to vaporize, turn from liquid to gas, and overcome those intermolecular forces. So it takes a higher temperature to get them to boil. So the dipole moment is really a measure of the intermolecular forces. Basically, the stronger the intermolecular forces, the higher your dipole moment. Dipole moment is referred to as mu. I know last chapter we just talked about mu being the speed, but in this case it's the dipole moment. Sorry, chemists love to reuse their symbols. But the stronger the intermolecular forces, the higher the dipole moment and the higher the boiling point. So if you look at this table right here, you'll see different substances and their molar mass, because remember, molar mass also contributes to the strength of your London dispersion forces, which are intermolecular forces. But you can see the dipole moment here, and the higher the dipole moment, the higher the boiling point. Again, because these are attracting each other more, so it's harder to separate them and turn them into a gas. Next type of interactions is hydrogen bonding. So that happens between molecules that have an HF, HN, or HO. So water has hydrogen bonding. If you mix like ammonia and water, then it will have hydrogen bonding interactions between them. And so again, the idea is that, let's draw water right here. And so there's partial negative on the oxygen, partial positives on the hydrogens. Let's draw, for example, an ammonia. And so partial negative on the nitrogen, partial positives on the hydrogens. They would actually align themselves so that, the hydrogens are next to the nitrogen. There's an attraction between the partial positive and the partial negative. It's a special type of dipole, but the partial positives and partial negatives in here are a little bit stronger, and so it is just slightly stronger than dipole interactions. Because of hydrogen bonding, because of how strong they are, it explains why water is so unique. For example, water, based on the size of it and how many electrons it has, it should really exist as a gas. But it really exists as a liquid because of the strong hydrogen bonding. Also, water is unique because ice floats. So ice is less dense than water. Let's write those down. Ice less dense than water. That's because in water the particles are free to slide around each other, and so they fit in all those nooks and crannies to get really close to each other because they're so attracted, and so that makes it just slightly more slightly more dense compared to the solid ice. The particles are really close to each other, but they have to maintain that nice crystal lattice, and so they can't really move in very close into these nooks and crannies and get really close like in liquid water. So we said ice is less dense than water. We said water is liquid at room temperature. Another thing is the extreme high surface tension of water, and because of that, the water can go up in the roots of the plants to make them survive, so that the capillary action is because of surface tension. What else? Ice being less dense than water keeps our ocean life. So when water freezes, when it's really cold, the ice floats, and so the warmer water stays on the bottom for all the sea creatures and living things to stay alive there. That's also how we maintain the temperature or the climate on our planet, is because of the large bodies of water. Water having strong hydrogen bonding allows very high heat capacity. It also allows very high heat of vaporization. That means it takes a huge amount of energy to change the temperature of water. Or vice versa, it needs to release lots of energy before its temperature cools down. And so the temperature on Earth remains relatively steady. This also explains the ionization of strong acids. So if you remember, acids are all covalent. So if you have something like, HCl, for example, this is covalently bonded. There are no ions. However, because of hydrogen bonding in water, the water is, since this has partial positive and partial negative, the water is able to come in and attract the chlorine enough that it actually pulls it away as Cl minus, just like it does with the ionic substances. And same thing with the hydrogen. The water is strong enough that the oxygen portion of the water can actually pull the hydrogen away as H+. So even though these are covalent, they will ionize because of the strength of the intermolecular forces of water, because of those strong partial positive and partial negatives. Just a reminder, our strong acids, there's 6 of them. There's HBr, HCl, HI, so all of the halides except for fluorine. There's nitric acid, there's sulfuric acid, and then HClO4. And just a reminder also, sulfuric acid is only the first hydrogen that's very strong, that completely dissociates 100%. The rest, the other hydrogen is not strong, it's actually weak. One last thing to look at on this page here is this graph. So this is showing hydrogen bonding. So H2O and HF both have hydrogen bonding. If you look at very similar molecules that have hydrogen with other elements in the same group as oxygen or in the same group as fluorine, these are their boiling points. And so you can see that HF and H2O have extremely high boiling point compared to hydrogen bonded to the elements in their group, because these have hydrogen bonding, whereas these just have dipole interactions. So hydrogen bonding is definitely stronger than regular dipole interactions. Next type of interactions are London dispersion forces, also known as induced dipole. So an example of that would be like we mentioned before, iodine and hexane. So both of these are nonpolar molecules. So again, London dispersion is the same thing as induced dipole. And the reason why it's called induced dipole is because, remember, we already talked about this with chlorines a little bit ago. So we said, if you have two molecules that are nonpolar, their electron clouds are pretty evenly distributed. If for just a small instant the electrons are in one area of the molecule more than the other, that gives that area a partial negative, and then this one a partial positive. And so because of that, it induces the neighboring molecule to do the same. And so it makes this molecule do the same thing because this is partially positive, so it pulls the electrons in this one towards it. And so now both of them have a partial positive, partial negative, and so there's an attraction right there. So that's why it's called induced dipole, because that dipole is induced by another molecule. Again, it happens only for an instant, and it happens between all of the molecules. Polarization is the extent to which that induced dipole is. So it's the extent to which the electron clouds are distorted by an instantaneous external charge. So how much you're inducing the dipole is called polarization. So high polarization means that you get a lot of distortion or a lot of London dispersion. Low polarization means very low London dispersion. So if you look at the next table here, this chart right here lists the gas and the boiling point. Notice these are all noble gases. The difference is how many electrons they have. And so the higher the number of electrons, the higher the boiling point, because the higher the number of electrons, that means stronger London dispersion. And so this is a much higher boiling point than this one is, because radon gas and xenon gas, those gases are attracted a lot more than helium, for example, with its only 2 electrons. So the larger the atoms have greater polarization. That is kind of true, except the wording might be a little bit tricky. It's not about larger, it's really about the number of electrons. So the reason is because they have larger number of electrons to be distorted. Or dispersed unevenly. So you want to place the liquids in order of boiling point. And so if you want to rank their boiling points, basically you're ranking their intermolecular forces. So what you do is you look at the types of intermolecular forces that they would have. And so this one, I don't know if you remember, you got 1, 2, 3, 4 hydrogens all singly bonded. This is called butane. But butane has London dispersion forces. It's nonpolar, that's the only type they have. Water has hydrogen bonding and also London dispersion, but it's negligible. C2H5OH also has hydrogen bonding, but water has stronger hydrogen bonding than C2H5OH. The reason is because if you look at water, the oxygen is partially negative, this is partially positive, and so any part of this molecule is going to attract another molecule because you got partial positives and negatives all around. Whereas if you look at C2H5OH, I'm going to draw it down here. There are your two carbons. There's your hydrogen, your lone pair, and you have a bunch of hydrogens here. And so the oxygen here is partially negative. This hydrogen is partially positive. Maybe that carbon is slightly partially positive as well. But it's really this main end of the molecule that is partially positive or negative that would attract another ethanol molecule. So only a portion of the molecule has really that hydrogen bonding or that attraction to another molecule. This one, there's hydrogen bonding all around. It would attract another water molecule from anywhere. And so back to this question, the higher the intermolecular forces, the higher your boiling point because the particles are so attracted to each other, they don't want to separate to turn into gas. And so the highest boiling point would be water, followed by ethanol, followed by the butane. So this is the lowest. And then water is the highest. Okay, let's identify the intermolecular force for the following. So CH4 and CH4 mixed together. So that would be induced dipole, since both of them are London dispersion. We got water with methanol. So that would be, you can either call that hydrogen bonding or you can call it dipole. Li plus and water, that's an ion, that's a polar molecule, so we'd call that ion-dipole interactions. All right, that is it for today. Hope you have a fantastic rest of your day, and I will see you tomorrow.